Okay, so I want to revisit this idea of the upper and lower sums, and we're going to generalize a little bit more and talk about kind of cleaning up this whole idea a little bit for ourselves so we can understand it a little better and also kind of get down to the core of what we're trying to do. All right, so we have here upper and lower sums, and you have this idea of the delta x, or that was, in the case of our example yesterday, the 3 over n that we were looking at, or the b minus a over n once we generalized it. Okay, so the x coordinate, we start at the left side, that a, okay, because we're dealing with the interval from a to b. Okay, and this interval, delta x, is going to be the width of the rectangle that we're dealing with. All right, width of the rectangle. So same idea as what we were doing yesterday, except we're using some familiar notation, that delta x that we've used in the past. All right, so notice we start at a, we end up at b. Okay? We don't know how many of these little division points there are. All right, but we find that we start from A, we go to B, and they're all cut into nice evenly distributed rectangles. Okay, they're all the same width. Now, this is something that's kind of interesting because we were looking at the lower sums and the upper sums yesterday. All right. Notice it here, it says, because f is continuous, the extreme value theorem guarantees the existence of a minimum and a maximum value of the function in each subinterval. Okay, so as we look at those little intervals defined by the delta x's, all right, so here's that, plus delta x, plus 2 delta x, plus 3 delta x, plus 4 delta x, and so on. In each of those intervals, we know there's going to be a minimum value of the function and a maximum value of the function. Okay? Again, that's the extreme value theorem. It just says there's a highest and lowest value in every interval. Okay? Now, the notation we're going to use here is a lowercase m. See, f of lowercase m sub I is going to be our minimum value of f in that little subinterval. And f of capital M of I is going to represent our maximum value, okay, in each interval. So you'll notice here the lower sums, again, we're kind of generalizing some stuff that we looked at yesterday. The lower sums are going to be the sum of the function evaluated at the minimum in each interval times the delta x. That was the width, okay? So there's length times width. For our area of the rectangle, we're adding up all the rectangles again, okay? The upper sum, we're also doing length times width, but for the length, we're using the highest point in each interval. You might say, okay, well, that's got to give us a big difference. Okay? Here's the thing, though. As we create more and more and more intervals, what's going to happen to the max and min values in those intervals?
They get closer together.
They're going to get closer together. Okay? They're going to get closer together. Notice here, with this delta x in this image, here's the max value, here's the min value. If I found the areas of the rectangle that's drawn, as opposed to this rectangle, I'm going to get something a little different, okay? However, let's say I cut this interval in half. Well, the difference between the max and the min in this interval, if I'm using this rectangle or as opposed to this rectangle, is less. Okay? So notice if I'm using upper sums versus lower sums in the first example, there's going to be a difference. Here, if I cut the interval in half and I use upper sums and lower sums, the difference is not going to be quite as much. If I cut that interval in half again, here's the rectangle I would use for the upper sum. Here's the rectangle I would use for the lower sum. Notice the difference there is much, much smaller. Okay? So the more intervals I get, in other words, the smaller that delta x becomes, what's going to happen to my upper sums and my lower sums?
They're going to approach each other?
They're going to approach each other. Okay? And that actually brings us to the theorem that we're looking at here, which is the limits of the lower and upper sums. Okay? Let f be continuous and non-negative in the interval from a to b. The limits as n approaches infinity of both the lower and upper sums exist and are equal to each other. Okay? They exist and they are equal to each other. So what we just looked at, because the upper sums are approaching the lower sums, they're getting closer to each other. The smaller the skinnier we make those rectangles, the limit as n approaches infinity is actually going to be equal. Because the max and the min are going to be approaching each other. They're approaching equality as well. Does that make sense? Yes. Okay? So, the limit of the lower sums, the first one, is going to equal the limit of the upper sums, which is just the limit of capital S sub n, all right? The limit of the sum itself, okay? And basically what this is telling us here, you are free. Look at the last sentence here, okay? Notice they're using the squeeze theorem here to prove this. We're not going to prove this. But basically, you can pick any x value you want inside the interval. We don't have to use the max or the min. We could use the middle. Or we could use the one that's 2/3 of the max. Or 2/3 of the way between the max and the min. Or whatever. We could use any arbitrary x value in the subinterval. Okay? And that allows us to get to this definition of the area of a region in the plane. Okay? The definition of the area of a region in the plane. Let f be continuous and non-negative in the interval from a to b. The area of the region bounded by the graph, the x-axis, and the vertical lines that define the two sides of your interval. In our example here, there's a, here's the function, here's the vertical line at b, and here's the x-axis. So the area we are trying to find here would be this area here. Okay? That area is given by this definition. Okay? The limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I delta x. And notice here the notation, it's where c sub I is between x sub I minus 1 and x sub I. In other words, it's between the two boundaries of the subinterval. Okay? And also they define delta x, as we saw yesterday, as the width of the rectangle. It's b minus a over whatever n is. Okay? Now, I know this is kind of theoretical here, all right, but it becomes practical as we try some. Okay? So let's talk about finding the area by definition. Okay, finding the area by the limit definition. So this is the limit. The limit as n approaches infinity of the sum from I equals 1 to n of, and let's look at the definition. The definition was f of c sub I times delta x, right? Let's sketch what we're given first of all. We're told that we're looking at the function y equals x cubed, which looks like this. The x-axis and the vertical lines x equals 0 and x equals 1. So let's say this is 1. Obviously this is 0. Okay, so the interval or the area that we are looking for is going to be the area in this part right here. Okay? Now it kind of looks like a triangle, but we know that the x cubed is curved. So we're going to need to use this definition. Okay? Now let's go ahead and plug in what we know. How can we find delta x, first of all?
1 minus 0 divided by n.
1 minus 0 divided by n, b minus a over n. So this is simply 1 over n. Okay, so now that we have the width of each rectangle, 1 over n, we'll plug that in. 1 over n, limit as n approaches infinity of the sum from I equals 1 to n of the f of c. Now the f of c part, we need to find a particular x value in the ith subinterval. Okay, so we have these subintervals, all these subintervals and so on. We don't know how many there are, but you'll notice what we could do is we could make the x coordinate just be I divided by however many rectangles we have. Okay, and that'll be different as it goes on. So what that means is that f of I over n, since f of x equals x cubed, will be I cubed over n cubed. All right, and that's the key to this whole thing. So we have I cubed over n cubed. Now you'll notice we can simplify a little bit here. Again, we're finding this area of that green region, so it's the limit as n approaches infinity. And I'm going to take out the constants. You'll notice I have a 1 over n, and I've got the I cubed over an n cubed. Those n's are all constants. I'm going to pull this out as a 1 over n to the 4th. And that leaves me with the sum from I equals 1 to n of just the I cubed. And that's where we were trying to get to. All right, at this point I can use the formula for the I cubed. I'm going to find the limit as n approaches infinity of the 1 over n to the 4th, and then the limit, or I'm sorry, the formula for the sum of the cube integers is n squared times n plus 1 squared all over 4. All right, so the first thing I'll do as I go to simplify this, I'm going to cancel that out and I'll just have an n squared on the bottom. I'm also going to FOIL the numerator because that'll help me as I take the limit as n approaches infinity. So the limit as n approaches infinity of n squared plus 2n plus 1 over a 4n squared. And now, because n is approaching infinity, these parts really don't matter because they're so minuscule compared to where the n is squared. I look at the leading coefficients because the degrees are both 2, and I end up with the limit equaling 1/4. So our area is 1/4. Let's try one more here and take a look at what that would look like. All right, here we're given a sketch. We're finding the area of the region bounded by the graph of f of x equals 4 minus x squared. As you can see, the x-axis and the vertical lines x equals 1 and x equals 2. Now this one, when we go to find the c sub I, it's going to be just slightly different because the previous one was starting from 0. This one's starting from 1. Okay, so while I'm mentioning that, anyways, the c sub I, we're starting at 1, and I'm going to make this the interval. Each interval is going to be I divided by n, but we're going to let the x is then going to be 1 plus I over n. All right, so if we're finding this rectangle, right here, we have the right-hand side is 1 plus I over n. In our case here, the f of c sub I then, that's our c sub I, our arbitrary value of x. This is going to be a 4 minus a 1 plus I over n quantity squared, because our function is 4 minus x squared. All right, so now we've kind of laid the groundwork for this. Let's start with our definition and build up to where we're actually going to use this. Okay, so the area is the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x. Okay, now we already figured out what f of c sub I is. I need to figure out what delta x is. And remember, delta x is b minus a over n. Well, b in this case is 2 because we're going from x equals 1 to x equals 2, and a is 1. And you'll notice here 2 minus 1 is 1 over n. So delta x is 1 over n. Now, it's not always going to be that, it just happens to be in the two examples we're doing. So now I'm taking the limit as n approaches infinity of the sum from I equals 1 to n of the f of c sub I. So we have a 4 minus 1 plus I over n squared, all times 1 over n. Now I've got to do some algebra here and see what I can do with it, okay? First of all, I'll go ahead and pull out the 1 over n. That'll make life a little bit easier. N approaches infinity of 1 over n. And now in the sum, I'm going to FOIL what's in the brackets, and I'm also going to combine it with that 4. So I'm going to have 4 minus 1, which is just going to be 3. And then I'm going to have an I over n plus an I over n, so it's 2I over n. So I'm subtracting a 2I over n. And then it's going to be minus the I over n times I over n. So I squared over n squared. Okay, so I'm taking the limit of that whole thing. Let's keep going. The limit as n approaches infinity of 1 over n, and at this point I'm going to split this into 3 separate sums. The sum from I equals 1 to n of 3, the constant, minus 2 over n. Notice that's the constant part of this middle term. The constant part is the negative 2 over n. I is the variable. So I'm going to then have the sum from I equals 1 to n of just I minus 1 over n squared times the sum from I equals 1 to n of the I squareds. Now notice here, this is happening a lot. When we're working with these sums, we want to get down to something that we have a formula for. Alright, whether it's a constant, or we had this constant multiples that we pulled out, and then all that's left in the sums are i's or I squareds or an I cubed that we have formulas for. Alright, so at this point it's time to use the formulas that we know. Alright, so we're still taking the limit as n approaches infinity. We still have that 1 over n, but let's look at what's in the brackets. This is going to be 3n. Okay, formula for a constant, it's just 3 times the n. Then we have a minus 2 over n, and the formula for the sum of the i's is n times n plus 1 over 2. Okay, so then notice that's going to simplify pretty nicely. The n over n cancels, the 2 over 2 cancels, and I just have a minus n plus 1. Then we have a minus 1 over n squared times the formula for the I squared. Remember, this is the one that's a little bit different. We've got an n times an n plus 1, like all 3 of the formulas do, but then it has this other set of parentheses, 2n plus 1, and it is over 6. Alright, so we've got a little bit of simplifying. This n, one of the n's on the bottom will cancel out that n. And now we're able to do a little bit more simplifying. Okay, limit as n approaches infinity of 1 over n bracket 3n minus n minus 1. And this is going to be a minus, there's going to be a 6n on the bottom. And on the top, we've got a 2n squared plus 3n plus 1. Doing a little bit more simplifying. Three n minus n is 2n minus 1. Now what I'm going to do here is I'm actually going to break this up into 3 separate fractions and simplify each one. Now when I do that, I need to make sure I distribute the negative. So my first one is going to be a minus 2n squared over 6n. It's going to just be n over 3. Then I have a minus 3n over 6n is a minus 1/2. And then I have a minus 1 over 6n, which is just 1 over 6n. Okay, so I split up these 3 pieces, put them all over 6n, and reduced them down to here. I also made sure to distribute the negative to all 3 parts. Now, let's keep going. Come up here a little bit. The limit as n approaches infinity. And at this point, I'm going to distribute in the 1 over n. Alright, so that's just going to be a 2 minus a 1 over n minus a third minus a 1 over 2n minus a 1 over 6n squared. And at this point, we can take the limits, and anything that has the n on the denominator is all going to come out to be 0 as n approaches infinity, because 1 over infinity is approaching 0. Alright, so that's going to be a 0, that's going to be a 0, that's going to be a 0, and we get just a 2 minus 1/3, which is 1 2/3. So that is the area that we are looking for, 1 2/3. So a lot of work, a lot of kind of tedious algebra. You've got to be careful, but that's how we can use the definition of the area with the sums and the sum properties that we've looked at to find the area under a curve.